What if I told you that Tesla just quietly revealed a battery technology so revolutionary, it could make every electric car on the road today obsolete overnight? And I'm not talking about some far-off laboratory experiment that'll take 20 years to commercialize, or another piece of vaporware that sounds impressive in press releases but never sees production. This is real, it's validated, it's happening right now, and it's about to turn the entire automotive industry completely upside down in ways that most people haven't even begun to understand. In the next 18 minutes, I'm going to break down Tesla's game-changing aluminum-ion battery technology that's powering the upcoming 2026 Model 2, and why this isn't just another incremental upgrade or marketing gimmick, but a complete paradigm shift that could end lithium's dominance forever and reshape the global energy landscape. By the end of this video, you'll understand exactly how this revolutionary technology works at the molecular level, why it's not just faster but 10 times more efficient than anything we've seen before, what the economic implications mean for consumers worldwide, and how this breakthrough could accelerate the transition to sustainable energy by decades rather than years. Welcome back to Tesla Torch, where we dive deep into the cutting-edge innovations that are shaping our electric future and changing the world one breakthrough at a time. If you're ready to discover the technology that industry insiders are calling the most significant advancement in energy storage since the invention of the battery itself, make sure to hit that like button and subscribe for more Tesla insights and analysis you won't find anywhere else on YouTube. Let's start with some uncomfortable truths about lithium-ion batteries that the mainstream media doesn't want you to fully grasp. For over a decade, lithium-ion technology has been the undisputed king of portable energy storage, powering everything from your smartphone and laptop to the Tesla Model S and every other electric vehicle on the market today. But here's what most people don't realize. Lithium is rapidly becoming a massive bottleneck that's not just limiting the growth of electric vehicles, but actually holding back the entire global transition to sustainable energy. Consider the geopolitical nightmare we've created. 70% of the world's proven lithium reserves are concentrated in just 3 countries: Chile, Australia, and Argentina. But here's where it gets even more concerning. 85% of global lithium processing and refining capacity is controlled by China. We've essentially traded dependence on Middle Eastern oil for dependence on Chinese lithium processing. And anyone who's been paying attention to global politics over the past few years knows that this is not exactly the energy independence and security that governments promised when they started pushing electric vehicle adoption. This creates a supply chain that's incredibly vulnerable to geopolitical tensions, trade disputes, price manipulation, and even natural disasters. When one country controls the majority of a critical resource's processing, they essentially control the entire industry that depends on it. And as global demand for electric vehicles increases exponentially, we're heading towards supply constraints that could make the semiconductor shortage of 2021 and 2022 look like a minor inconvenience. But the problems with lithium-ion technology go much deeper than just supply chain vulnerabilities. These are fundamental technical limitations that have been plaguing the technology since its inception, and despite billions of dollars in research and development, they haven't been solved. They've just been marginally improved. Current generation lithium-ion batteries, even the most advanced ones in Tesla's Model S Plaid, take 30 to 45 minutes for a full charge using the fastest available superchargers. That's not just inconvenient, it's a fundamental barrier to mass adoption. Think about your current relationship with gasoline vehicles. You pull into a gas station, spend maybe 4 or 5 minutes filling up, and you're back on the road with full rang. But with current electric vehicles, you're looking at a minimum 30-minute stop, and that's assuming you can find a working fast charger that isn't already occupied. The lifespan issue is even more problematic. Current lithium-ion batteries last about 8 years before they experience significant degradation that noticeably impacts range and performance. You're looking at maybe 2,000 full charge cycles if you're lucky and treat the battery extremely well. After that, you're facing a battery replacement cost that can easily exceed $15,000 for a premium vehicle. This creates a massive financial liability that hangs over every electric vehicle purchase like a sword of Damocles. Temperature sensitivity is another critical limitation that most consumers don't fully understand until they experience it firsthand. Lithium-ion batteries only work properly in a narrow temperature range between 20 and 30 degrees Celsius. Outside of that range, performance degrades rapidly, charging speeds slow down dramatically, and in extreme cold, the batteries can lose 50% or more of their effective range. This means manufacturers have to build complex thermal management systems with pumps, coolant, heaters, air conditioning, and sophisticated control electronics just to keep the battery operating within acceptable parameters. All of this adds significant weight, complexity, cost, and additional points of failure to every electric vehicle. It's engineering complexity that internal combustion engines don't require. And it's one of the reasons why electric vehicles are still more expensive than their gasoline counterparts. These limitations aren't just minor inconveniences that enthusiasts can overlook. They're fundamental barriers preventing mainstream consumers from making the switch to electric vehicles. Range anxiety isn't just about distance. It's about the time penalty of slow charging, the uncertainty of battery degradation over time, the fear of being stranded in extreme weather conditions, and the looming financial burden of eventual battery replacement. Now, imagine if I told you there was a battery technology that could completely eliminate every single one of these problems. A technology that could charge in 10 minutes instead of 45, last 27 years instead of 8, work perfectly in temperatures ranging from minus 50 degrees to plus 150 degrees Celsius without any thermal management and system, and cost 75% less to manufacture. You'd probably think I was describing some fantasy technology that exists only in science fiction, decades away from any practical implementation. But that's exactly what Tesla has achieved with their breakthrough aluminum-ion battery technology, especially when integrated with supercapacitors in what they're calling a hybrid dual-layer architecture. We're not talking about theoretical performance numbers or laboratory prototypes that work under perfect conditions. This is validated technology in pre-production prototypes that are already being tested in real-world conditions and are scheduled for mass production in 2026. The energy density breakthrough alone is staggering. We're talking about approximately 1,000 watt-hours per kilogram, which is more than double what the most advanced lithium-ion batteries can deliver today. To put that in perspective, current Tesla Model S batteries achieve around 400 to 450 watt-hours per kilogram under optimal conditions. This isn't a marginal improvement, it's a quantum leap that fundamentally changes what's possible in electric vehicle design. But energy density is just the beginning. The real breakthrough that makes this possible lies in something called graphene quantum dots. And understanding how these work is crucial to grasping why this technology represents such a revolutionary advance. Picture particles so incredibly small that they're just 1 nanometer in diameter. To put that scale in perspective, if a graphene quantum dot were the size of a basketball would be the size of the entire Earth. These are structures that exist at the absolute boundary between chemistry and physics, where quantum mechanical effects start to dominate material behavior. These microscopic marvels are strategically embedded within the battery's anode and separator layers, and their function is absolutely crucial to solving problems that have plagued battery technology for decades. In traditional lithium-ion batteries, something called dendrite formation occurs over time. Dendrites are essentially metallic whiskers or tree-like structures that slowly grow inside the battery during charging cycles. Think of dendrites like cancer in your battery. They start small, but they grow over time, eventually piercing through the separator that keeps the positive and negative sides of the battery apart. When that happens, you get internal short circuits, capacity loss, heat generation, and in the worst cases, thermal runaway that can cause fires or explosions. This dendrite formation is one of the primary reasons why lithium-ion batteries degrade over time and eventually fail. Graphene quantum dots prevent dendrite formation entirely by acting as molecular guides that direct electron flow along predetermined pathways. Instead of allowing metal ions to randomly deposit and form dendrites, the quantum dots create organized channels that keep the electrochemical reactions controlled and predictable. It's like the difference between water flowing through carefully designed irrigation channels versus flooding chaotically across a field. But here's where the physics gets truly mind-blowing. These quantum dots reduce internal resistance within the battery by up to 95%. Internal resistance is basically the battery fighting against itself. Energy that gets converted to waste heat instead of being delivered to the motor. Reducing internal resistance by 95% means that 40% more of the battery's stored energy actually reaches the wheels. And charging can happen up to 10 times faster because the battery isn't fighting against its own internal resistance. And here's perhaps the most remarkable part about this entire breakthrough. You know how much of these graphene quantum dots is required per battery pack? 1 gram. That's equivalent to a single grain of rice completely transforming an entire vehicle's energy system. The cost impact is negligible, but the performance impact is revolutionary. The genius of Tesla's approach lies in what they call a 2-layer hybrid architecture that combines the best characteristics of 2 different energy storage technologies. The aluminum-ion layer provides steady, reliable power for daily driving. Think of it as the marathon runner of your battery system. This layer handles all your normal driving needs: highway cruising, city commuting, running air conditioning and heating, powering all the vehicle's electronics. Meanwhile, the supercapacitor layer acts like a sprinter, delivering massive bursts of power for acceleration and immediately absorbing energy from regenerative braking. When you floor the accelerator, for highway merging or track performance, the supercapacitor layer provides instantaneous power delivery that would be impossible with chemical batteries alone. When you hit the brakes, instead of losing that kinetic energy to heat like in a gasoline car, the supercapacitor layer captures it almost instantaneously and stores it for the next acceleration event. This fusion architecture means that drivers no longer have to choose between range and performance, between efficiency and excitement, between practical daily driving and weekend fun. You literally get both optimized simultaneously, which represents a fundamental breakthrough in electric vehicle engineering. But Tesla didn't stop at just creating better battery chemistry. They've developed something that borders on science fiction, a battery system with sophisticated artificial intelligence built directly into its core architecture. Sitting beneath the center console of the Model 2 is Tesla's proprietary quantum neural processing chip, designated QNP1. This isn't just a simple battery management system that monitors voltage and temperature. This is a full artificial intelligence system that's learning, predicting, and optimizing your driving experience in real time. Using GPS history, driving pattern analysis, eye movement tracking through the cabin cameras, and even muscle tension sensors embedded in the steering wheel and seat, QNP1 builds a comprehensive behavioral model of how you drive. It learns that you typically accelerate aggressively when merging onto highways during your morning commute. It knows that you take a specific mountain road every Saturday morning where you enjoy spirited driving. It understands that you're usually in efficiency mode during long road trips, but prefer maximum performance around town. This predictive intelligence allows the system to pre-optimize battery performance with 85% accuracy. If the system knows you're approaching a highway on-ramp where you typically accelerate hard, it pre-charges the supercapacitor layer and adjusts the aluminum-ion chemistry for maximum power delivery. If you're starting a long highway journey, it optimizes for maximum efficiency and range. If you're pulling into your driveway and the system knows you typically don't drive again until morning, it begins preparing for overnight conditioning cycles. The results are remarkable: 25% improvement in OV, roll battery efficiency, and 30% reduction in long-term wear and degradation. We're talking about extending optimized charge cycles to 1,200 to 1,500 cycles beyond what would normally be possible, purely through intelligent management. But the QNP1 chip's capabilities extend far beyond just battery optimization. It enables real-time biometric feedback that allows the vehicle to adjust not just energy management, but the entire driving experience based on your physical and emotional state. Through sensors that monitor heart rate variability, stress indicators, fatigue levels, and even micro-expressions captured by the cabin cameras, the Model 2 can modulate suspension settings, throttle response mapping, steering weight, ambient lighting, and even audio system tuning. If the system detects that you're stressed from a difficult day at work, it might soften the suspension, reduce throttle sensitivity to make the car feel more relaxed, and adjust the cabin lighting to more calming colors. If it detects that you're alert and energetic, it might sharpen the suspension, increase throttle response, and optimize the display layouts for a more engaging driving experience. This isn't just a car adapting to road conditions. It's a vehicle that adapts to your emotional and psychological state in real time. Now let's talk about the materials revolution that makes all of this economically viable. The shift from lithium to aluminum isn't just about performance. It's about fundamentally restructuring the global supply chain in a way that benefits consumers, reduces geopolitical risks, and supports truly sustainable manufacturing. Aluminum is the third most abundant element in Earth's crust and the most abundant metal. Global reserves exceed 700 million metric tons, and unlike lithium, aluminum deposits are widely distributed across every continent. The United States alone produces 1.7 million tons of aluminum annually, and unlike lithium mining, which often involves environmentally destructive brine evaporation or hard rock mining, aluminum is primarily extracted from bauxite through well-established, relatively clean industrial processes. But here's the real game changer. Aluminum can be recycled indefinitely without any loss of performance characteristics. Every aluminum can you've ever recycled can potentially become part of a battery that powers an electric vehicle. This creates a true circular economy where the raw materials for batteries can be sourced entirely from recycled content, eliminating mining altogether once sufficient aluminum is in circulation. The economic implications are staggering. Aluminum-ion batteries use simpler cell structures, require fewer exotic materials, and can be manufactured using faster, more automated processes. Tesla's engineering teams have eliminated the need for expensive cobalt, reduced dependence on lithium, and created battery architectures that can be assembled with 97% automation. Manufacturing costs drop by up to 75% compared to current lithium-ion technology. A typical $15,000 battery pack for a premium electric vehicle could drop to less than $4,000. This isn't just an incremental cost reduction. It's the difference between electric vehicles being luxury items for affluent early adopters and being accessible to mainstream consumers worldwide. But the real engineering masterpiece lies in how Tesla has created a hybrid battery system where aluminum and lithium ions work in perfect electrochemical harmony. Inside the 2026 Model 2, they've developed what they call a dual-ion transport architecture that leverages the best characteristics of both elements while eliminating their individual limitations. The foundation of this system is an ultra-thin aluminum substrate layer that completely replaces the copper current collectors used in traditional batteries. Copper is heavy, expensive, and prone to corrosion over time. The aluminum substrate is lighter, cheaper, and actually improves electrical conductivity while providing better structural stability for the active battery materials. The graphite anode, which stores energy during charging, is coated with precisely engineered aluminum nanoparticles that boost ion flow rates by 60%. These nanoparticles create additional pathways for electrical charge to move through the battery, reducing bottlenecks and allowing for much faster charging speeds without generating excessive heat. The cathode design is even more sophisticated. It's engineered as a layered sandwich structure combining aluminum foil, specialized carbon paper, and lithium ion-based active materials. This layered architecture dramatically reduces energy loss during charge and discharge cycles, while providing exceptional structural stability over hundreds of thousands of cycles. In this hybrid system, lithium ions act like scouts or pathfinders, guiding the overall charge and discharge processes and maintaining the electrochemical stability of the system. Meanwhile, aluminum ions deliver the heavy lifting in terms of actual energy storage and power delivery. This division of labour allows each element to operate in its optimal range while compensating for the other's limitations. The dual ion transport enables synchronized charge and discharge patterns that deliver up to 1200 watt-hours per kilogram. Nearly 4 times what standard lithium-ion cells can achieve today. But the real magic happens in how this hybrid system manages and maintains itself over time. Tesla has engineered what they call a self-repair mechanism into the battery's fundamental architecture. Aluminum particles can actually migrate within the battery structure during normal operation to seal microscopic fractures and imperfections that develop over time. It's like having a battery that can heal its own wounds at the molecular level. Meanwhile, lithium ions maintain what Tesla describes as a dynamic protective layer, essentially a constantly renewing interface that prevents degradation reactions and maintains optimal performance characteristics. The liquid electrolyte system flows throughout the battery like blood through a circulatory system, automatically restoring electrical contact, removing impurities, and optimizing ion concentrations in real time. This self-healing capability allows the battery to actually improve its performance over time rather than degrading. The system can hibernate during extended periods of non-use, preserving 95% of its charge for over 6 months while maintaining all active protective systems. When you return to the vehicle, the battery wakes up in just 0.3 of a second, fully ready for normal operation. An integrated AI algorithm constantly monitors temperature, usage patterns, charging behavior, and even driving style, then dynamically shifts the balance between aluminum and lithium-ion activity for optimal performance under any conditions. The system operates in up to 47 distinct modes, each optimized for specific combinations of temperature, power demand, charging state, and battery age. During cold weather operation, the system might favor aluminum-ion chemistry, which performs better at low temperatures. During high-performance driving, it might shift toward lithium-ion processors, which deliver superior power density. During efficiency-focused highway cruising, it finds the perfect balance to maximize range. This level of adaptive, intelligent management is completely unprecedented in any manufactured product, let alone automotive batteries. Safety has always been a primary concern with high-energy battery systems, but Tesla's engineering team has developed solutions that seem to defy conventional wisdom about battery safety. Their advanced polymer separator system can detect physical damage in real time and automatically contract to seal breaches, restoring over 93% of structural integrity in less than 1 second. Think about the implications of this. In traditional batteries, any physical damage to the separator, whether from manufacturing defects, thermal expansion, dendrite formation, or external impacts, can lead to catastrophic failure. Tesla's self-sealing separator essentially eliminates this failure mode entirely. The overall architecture is completely modular, designed around 64 individual microcells arranged in what Tesla calls a fractal layout. Each microcell operates independently and can be isolated from the rest of the system if problems develop. Instead of replacing an entire battery pack that might cost $15,000, technicians can replace individual microcells for a few $100s each. This modular design also enables partial battery upgrades over time. As battery technology continues to improve, owners could theoretically upgrade just portions of their battery pack rather than replacing the entire system. It's like being able to upgrade your laptop's RAM without buying an entirely new computer. But perhaps the most remarkable aspect of Tesla's aluminum-ion battery is what they call synthetic intelligence. The battery literally behaves like a distributed nervous system. Embedded throughout the battery structure are 248 nanoscale sensors, each capable of monitoring ion movement, temperature gradients, pressure variations, electrical resistance, and even microscopic structural changes. These sensors collect data at a RA, 8 of 10,000 samples per second, creating a real-time map of everything happening inside the battery at the molecular level. Advanced AI algorithms process this data stream to predict component failures, optimize performance, and automatically implement corrective measures up to 72 hours before problems would normally become apparent. The predictive maintenance capabilities are extraordinary. The system can detect the early stages of potential problems, things like unusual ion migration patterns, microscopic structural fatigue, or subtle changes in electrical resistance, and automatically trigger countermeasures. These might include microelectrical pulses to redistribute ions, localized heating or cooling to optimize chemical reactions, or adjustments to charging patterns to reduce stress on specific battery regions. The battery adapts its behavior based on your driving patterns and preferences. If you typically drive aggressively and demand high performance, it optimizes for power delivery and heat management. If you prioritize efficiency and gentle operation, it focuses on maximizing range and longevity. If you have predictable daily routines, it pre-optimizes charging and thermal conditioning to be ready when you are. The system executes over 847 unique response patterns, with behavior algorithms that adjust based on time of day, driving habits, climate conditions, battery age, and even seasonal patterns. This level of behavioral complexity and autonomous operation is something we've never seen in any consumer product. It's artificial intelligence applied to battery management in ways that seemed impossible just a few years ago. Tesla's quantum pulse technology represents another fundamental breakthrough that addresses what many experts consider the real bottleneck in electric vehicle performance. Not just how fast you can charge the battery, but how consistently the battery can deliver power under demanding conditions. Traditional lithium-ion batteries suffer from what's called power fade under high load conditions. When you demand maximum acceleration, towing power, or sustained high-speed driving, the battery's ability to deliver power diminishes over time within each drive cycle and degrades permanently over many cycles. This is why many electric vehicles feel peppy when the battery is fresh and fully charged, but becomes sluggish as the battery ages or depletes. Aluminum ions form crystalline lattice structures that actually grow stronger and more organized with repeated use. Instead of degrading under stress like lithium systems, aluminum-ion batteries maintain 100% power consistency across 10,000 full-throttle acceleration cycles. The cells actually operate at optimal efficiency when running at 85 degrees Celsius, temperatures that would damage lithium batteries, which means they perform better when hot rather than requiring complex cooling systems. The adaptive power scaling system means the battery delivers precisely the right amount of energy for any driving condition, reducing waste by 15% compared to fixed output systems. When you're cruising efficiently on the highway, it provides exactly enough power without over-delivering. When you need maximum acceleration for highway merging or emergency maneuvers, it instantly scales to full output without the power fade that affects lithium systems. Regenerative braking efficiency reaches 98% energy capture, which means nearly all the kinetic energy from slowing down gets converted back into stored electrical energy. In mountainous driving, this can actually result in arriving at your destination with more charge than when you started climbing. Traditional vehicles waste all of this energy as brake heat, but Tesla's aluminum-ion system turns every downhill section into a charging opportunity. The charging breakthrough that's captured the most attention comes from Tesla's hypercharged nanolattice architecture within each individual cell. This nanoscale structure allows aluminum ions to move through the battery material up to 10 times faster than lithium ions can move through traditional battery materials. The result is verified 0 to 80% charging in just 5 minutes under real-world conditions, not laboratory-ideal scenarios. That's faster than filling up a gasoline tank, and it completely eliminates range anxiety as a barrier to electric vehicle adoption. Even better, this charging speed doesn't diminish as the battery ages. The nanolattice structure maintains its performance characteristics across hundreds of thousands of charge cycles. The nanolattice design also dissipates heat 50% more efficiently than any existing battery architecture, which means the system remains stable and safe even during ultra-rapid charging in extreme temperature conditions. This thermal management efficiency is crucial for global deployment in climates ranging from Arctic conditions to desert environments. Industry analysts believe this charging breakthrough alone could trigger the conversion of 40% of gasoline vehicle owners to electric vehicles within the next 5 years. When charging becomes faster than refueling and the total cost of ownership drops below gasoline vehicles, the economic incentives become overwhelming for most consumers. The geopolitical implications are equally significant. This technology represents a massive shift away from China's dominance of lithium processing and toward domestically abundant aluminum resources. Countries that have felt vulnerable to supply chain disruptions in critical battery materials can now develop energy storage industries based on locally available resources. To support this revolution in battery technology, Tesla is constructing what they call Gigafactory 2.0. A completely reimagined approach to battery manufacturing that's designed specifically for aluminum-ion production. These facilities are engineered to produce 500,000 battery packs annually, which represents 10 times Tesla's current battery manufacturing capacity. The production process achieves 97% automation through advanced robotics and AI-controlled quality systems. By 2027, Tesla plans to have over 100 of these facilities operational worldwide, including specialized micro-gigafactories in 20 different countries to reduce shipping costs and support local employment. Production costs are projected to reach $40 per kilowatt hour, which makes supercar-level performance affordable for mass-market vehicles. For comparison, current lithium-ion battery costs are around $130 to $150 per kilowatt hour. So we're looking at a dramatic cost reduction that fundamentally changes the economics of electric vehicles. Tesla's AI-driven supply chain optimization focuses on aluminum sourcing from recycled materials and enables 95% of all battery materials to be recycled on-site. This creates a closed-loop manufacturing system that eliminates waste, reduces environmental impact, and completely removes dependence on foreign supply chains for critical materials. The ripple effects of this manufacturing revolution extend far beyond automotive applications. The same aluminum-ion battery technology will power next-generation home energy storage systems, grid-scale utility installations, portable electronics, and even aerospace applications. Tesla projects that by 2028, their aluminum-ion batteries could be supplying 5% of global electricity storage capacity. When we examine the Model 2 specifically as the first vehicle to showcase this revolutionary technology, the performance specifications read like science fiction. 550 miles of EPA-rated range from a battery pack that weighs 40% less than current lithium systems. 0 to 60 mile/hour acceleration in under 4 seconds, despite being positioned as an affordable mass-market vehicle. 5-minute charging that adds 400 miles of range, making long-distance travel faster and more convenient than with gasoline vehicles. The starting price of $15,759 positions the Model 2 not just as a competitive electric vehicle, but as one of the most affordable new cars available in any category. When you factor in lower maintenance costs, no fuel expenses, and the 27-year battery lifespan, the total cost of ownership becomes significantly lower than any gasoline vehicle. Compare these specifications to current competitors like BYD's Dolphin, which starts at $21,000 but offers only 200 miles of range and requires 25 minutes for charging. Or consider the Nissan Leaf at $28,000 with 150 miles of range and 40-minute charging times. The Model 2 isn't just incrementally better than these vehicles, it's operating in a completely different performance category while costing significantly less. Tesla's production projections of 4 million Model 2 units annually by 2030 would represent the largest manufacturing scale-up in automotive history. This volume would drive global electric vehicle market penetration from the current 8% to over 30% within the decade, fundamentally reshaping transportation worldwide. The aluminum-ion battery's exceptional durability, rated for 500,000 full C-Harge cycles representing over 100 years of typical driving patterns, combined with its affordability, makes electric vehicles accessible in markets that have been completely excluded from EV adoption due to economic constraints. We're talking about enabling electric vehicle ownership in developing countries where current EV prices are completely out of reach for average consumers. But the Model 2 represents more than just individual transportation. It's designed as a mobile energy node that can actively participate in electrical grid management and energy distribution. With ultra-fast charge and discharge capabilities, these vehicles can absorb excess renewable energy during peak production periods and feed power back to the grid during peak demand. By 2026, analysts project that urban electric vehicles could collectively provide up to 12% of city electrical grid stabilization capacity. This bidirectional power flow capability transforms every electric vehicle from an energy consumer into an active participant in the electrical grid, supporting renewable energy integration and improving overall grid resilience. The climate versatility of aluminum-ion batteries is crucial for global deployment strategies. These systems operate reliably in temperature ranges from -50 degrees Celsius to +80 degrees Celsius without requiring any thermal management systems. This universal climate capability eliminates the need for different battery configurations for different markets and enables standardized global production. This temperature resilience is particularly important for Elon Musk's vision of autonomous vehicle fleets and robotaxi networks operating in diverse climate conditions worldwide. Current electric vehicles require significant modifications for cold climate operation, adding cost and complexity. Aluminum-ion batteries eliminate these constraints entirely. Autonomous fleet operators stand to benefit enormously from aluminum-ion technology. The projected savings of $12,000 per vehicle lifecycle through eliminated battery replacements and reduced maintenance downtime, multiplied across fleets of millions of vehicles, represents hundreds of billions in operational cost reductions that can be passed through to consumers as lower transportation costs. One of the most frequent questions from current Tesla owners concerns retrofit compatibility. Whether existing vehicles can be upgraded to aluminum-ion battery technology. This is a complex engineering challenge because traditional lithium-ion battery packs are permanently integrated into vehicle structures and the vehicle's electronic systems are hard-coded for specific battery chemistry characteristics. However, leaked Tesla service documentation references something called a cross-platform module interface, or CPMI, which suggests that Tesla has been designing their vehicle architectures with future battery technology upgrades in mind. This system would theoretically allow compatible Tesla vehicles to receive aluminum-ion battery upgrades through specialized service procedures, though the technical details and eligible vehicle models haven't been officially announced. The implications of retrofit compatibility extend beyond individual vehicle upgrades. If existing Tesla vehicles can be integrated into Tesla's distributed energy network through battery upgrades, it would create a massive installed base of grid-connected energy storage almost overnight. This could accelerate the deployment of vehicle-to-grid technology and renewable energy integration by years, compared to waiting for natural vehicle replacement cycles. Tesla's direct-to-consumer manufacturing and sales model enables unprecedented customization and rapid deployment of new technologies. The company offers 847 million possible vehicle configurations through their online ordering system, with delivery capabilities anywhere in the world within 72 hours of order confirmation. The subscription-based ownership models that Tesla is developing allow consumers to lease battery technology separately from the vehicle, or to upgrade to the latest battery innovations annually, rather than waiting for complete vehicle replacement. This flexibility makes cutting-edge technology accessible to consumers who might not be able to afford the full purchase price up front, while ensuring that vehicles can stay current with rapidly evolving battery technology. These flexible ownership models also support Tesla's vision of transforming personal transportation from a product that consumers own to a service that they access. In urban environments where many people don't need daily vehicle access, subscription models combined with autonomous driving capabilities could provide transportation services at costs significantly lower than current vehicle ownership. The broader implications of Tesla's aluminum-ion battery breakthrough extend far beyond the automotive industry into fundamental changes in how human civilization generates, stores, and uses energy. We're looking at technology that could accelerate the transition to renewable energy by decades, eliminate energy poverty in developing countries, and create new industries and economic opportunities worldwide. The shift from lithium dependence to aluminum abundance represents a geopolitical realignment that reduces resource-based conflicts and enables energy independence for countries that were previously dependent on foreign battery materials. The environmental benefits of infinitely recyclable aluminum versus mining-intensive lithium extraction could significantly reduce the environmental footprint of the transition to electric transportation. But perhaps most importantly, the cost reductions and performance improvements make electric vehicles accessible to billions of people who were previously priced out of clean transportation options. When a vehicle with supercar performance characteristics costs less than $15,000 and lasts for decades with minimal maintenance, it becomes accessible to global markets that current electric vehicles cannot serve. The manufacturing job creation potential is enormous. Tesla's planned network of 100-plus gigafactories worldwide, each employing thousands of workers in high-skill manufacturing jobs, represents one of the largest industrial build-outs in modern history. The economic multiplier effects of these facilities, supporting local suppliers, contractors, and service industries, could revitalize manufacturing regions worldwide. From a technological perspective, the artificial intelligence and materials science innovations that enable aluminum-ion batteries will likely find applications far beyond automotive use. The quantum dot manufacturing techniques, AI-driven battery management systems, and advanced recycling processes represent foundational technologies that could drive innovation across multiple industries. The timeline for this transformation is remarkably aggressive. With production beginning in 2026 and full-scale deployment targeted for 2030, we're looking at a complete stride transformation within the current decade. This isn't a distant future scenario. It's an immediate disruption that will affect every aspect of transportation, energy, and manufacturing within the next few years. As established automotive manufacturers scramble to understand and respond to Tesla's aluminum-ion breakthrough, they're discovering that this isn't just a new battery chemistry they can license and integrate into existing vehicle platforms. The entire approach to vehicle design, manufacturing, and ownership that Tesla has developed around aluminum-ion technology represents a systemic advantage that will be extremely difficult for competitors to replicate quickly. The integration of artificial intelligence, materials science, manufacturing automation, and energy management that enables Tesla's aluminum-ion systems represents years of coordinated development across multiple technical disciplines. Competing manufacturers who have been focused on incremental improvements to lithium-ion technology now face the prospect of rebuilding their entire technical approach from the ground up. The electric revolution that many analysts predicted would take 20 to 30 years to fully materialize may instead happen within the next decade, driven by technology that makes electric vehicles not just equivalent to gasoline vehicles, but dramatically superior in every meaningful performance category, while costing significantly less to own and operate. Tesla's aluminum-ion battery breakthrough represents the kind of technological discontinuity that reshapes entire industries and creates new economic paradigms. By solving the fundamental limitations of lithium-ion technology while dramatically reducing costs and improving performance, Tesla has created what may be the final piece of the puzzle for universal electric vehicle adoption. The implications reach far beyond just making better cars. We're looking at technology that could fundamentally change how human civilization uses energy, reduce geopolitical conflicts over natural resources, accelerate the deployment of renewable energy systems, and make clean transportation accessible to every person on Earth regardless of their economic circumstances. As the rest of the automotive industry works to understand what just happened, Tesla is already building the infrastructure to manufacture these revolutionary batteries at global scale. The electric future isn't coming gradually over the next few decades. It's arriving right now, and it's powered by aluminum. If this deep dive into Tesla's aluminum-ion battery revolution has been as eye-opening for you as it was for me to research, make sure to hit that like button and subscribe to Tesla Torch for more exclusive analysis and insights into the technologies that are reshaping our world. What aspect of this breakthrough are you most excited about? Are you planning to wait for the Model 2, or do you think other manufacturers will be able to compete with this technology? Let me know your thoughts in the comments below, and I'll see you in the next video where we'll explore what this means for Tesla's competition and how the traditional automotive industry is scrambling to respond to this technological earthquake.